Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module we will discuss boundary conditions for the electromagnetic field quantities E, B, D and H. What are these boundary conditions and why should one consider or one should study them? Now let us assume that this paper that I have separates two regions. This region where this pen for example could be present, okay, is what I call as region 1, where the material properties are described by a certain set of values for mu and epsilon. So let us say the region in this region here to this particular side of my hand, this is mu 1 and epsilon 1, where mu 1 is the relative or mu 1 is the permeability and epsilon 1 is the permittivity. There could also be conductivity, so let us call this as some sigma 1 in this region. Separated on this side, okay, on this side where my hand is showing, so I have a second medium which is mu 2, epsilon 2 and sigma 2. So these are described by the parameter values of the material mu 2, epsilon 2 and sigma 2. This boundary between the two mediums is actually very thin, although you can see that there is a certain amount of small thickness to the paper, okay, which in fact should exist in a real medium. In a real medium, this thickness of these papers that I have considered as the boundary between two regions will actually correspond to the few layers, few atomic layers or few molecular layers where the properties change continuously from mu 1 epsilon 1 sigma 1 to mu 2 epsilon 2 sigma 2. No change can be abrupt like a boundary. But if you are looking like from me using a telescope or whatever that is, or rather if you are looking at it from a distance, a few layers of molecules which might be about a few tens or hundreds of angstroms doesn't really bother you, because if you actually look at, for example, you take a lens, okay, a lens will have a certain glass property that would be different from the surrounding air medium. However, the thickness of the lens is so much larger compared to the few atomic layers, tens of atomic layers or tens of molecular layers thickness, that you can consider the thickness of the boundary that separates two medium to be almost equal to 0. So we call these as jump boundaries, and we call these boundary conditions as jump boundary conditions because the material properties jump suddenly from one value to another value, okay. And when such a thing happens, is there a guarantee that the electric fields, magnetic fields, D field, H field, whatever that we calculate in region 1 and we calculate them in region 2, are they related to each other or not? First of all, should they be related? If they are related, how are they related? That is precisely the subject of this module. To set the stage, okay, let me draw a line here and call this line as the dividing boundary between two regions. As we said, this is mu 1, sigma 1 and epsilon 1, although for now let me just focus on mu 1 and epsilon 1. We will talk of sigma 1 later because only one equation requires sigma 1. And suddenly on the other side of this boundary you have mu 2, sigma 2 and epsilon 2, okay. We have solved Maxwell here, okay, and Maxwell tells us that the fields here are given by the vector quantities E1 and H1, D1, B1. You can also have a J1 in case you wish to talk of the continuity condition for J, okay, but for now we will not worry about J, okay. So we have solved Maxwell's equations along with whatever the initial conditions that are necessary, and we have used the Maxwell's equations to come up to the corresponding values E1, H1, D1 and B1, okay. So these are the fields, and we have solved Maxwell in region 2 as well, where we obtain E2, H2, B2 and D2. These are all your vector quantities which vary both as a function of r, okay, which vary both as a function of r as well as a function of time. So all the field quantities are functions of space as well as time. So these are the time varying and space changing field quantities: electric field, magnetic field H or the magnetic field intensity H, electric flux density D and magnetic flux density B. Now that we have these equations with us, what is the relationship between E1 and E2? We are not interested only in the relationship between E1 and E2 here, we are also interested in the relation between the boundary, okay. So how does having electric field E1 in region mu 1 epsilon 1 and electric field E2 in region mu 2 and epsilon 2 and having a boundary separate the two regions relate the values of the electric fields E1 to E2. In order to understand that one, let us fix 2 points. Okay, so let us fix 2 points. Let us call this as point 1 and point 2, and I will also consider a unit vector in the direction from 1 to 2. Okay, you know that between any 2 points there will be a line, right? So you can always draw a line. So this is the line between any 2 points, and then between these 2 points there will be a bisection. For simplicity, let us actually take these points 1 and 2 in such a way that bisector happens to be just the boundary that you have considered. Okay, so between any 2 points you have a boundary. Okay, and in fact if you think of this as a 3-dimensional extension, right, you can see that this is actually defining a plane as well, right. So this is actually defining a plane as well. So you can imagine that I have 2 points here, and then there is a line here, and then there is essentially a plane that connects between these 2 points. So this is a situation that I am considering. So the point 1 is located here and point 2 is located on this particular side. Okay. Now by some means, we do not really know what those means are, we have calculated the electric field, let us call this as E1, and we have figured out that its direction at this particular time is given by this particular black arrow that I have written. Similarly, E2 we have calculated, and that also is seen to be having in this direction, or maybe we will erase this one and then get back to a simple thing that I would actually use to calculate the boundary condition. So I will orient my boundary in such a way that this is the boundary, because this makes my task little easier. Okay. So these are the 2 points, points 1 and 2, and we know that these 2 points essentially are bisected by the plane. Above this plane you have mu 2 and epsilon 2, below this plane you have mu 1 and epsilon 1. This is the same situation, I have just made the boundary horizontal rather than vertical, so that I can write the equations on this side. Okay. So I have considered the electric field to be, okay, let me consider this electric field over here to be calculated and pointing in this direction E1, and the electric field here to be pointing in this direction and having a certain value E2 here. Now what is the relationship between E1 and E2? In order to answer that, we need to go from what we call as the point form of Maxwell's equations into integral forms of Maxwell's equations. They are no more difficult than the point form, and for our benefit here, okay, we will just write down the integral forms. Okay, these integral forms are more basic, they are more fundamental, they will always hold even when the boundary is actually moving. Okay, it does not matter when the boundary is present or not, even when the boundary is moving, these integral forms are always valid. So what are the integral values? We know that del cross E, if you just go back and write down the curl expression in terms of the line integral over the closed path, is going to be nothing but E dot dl, right, and that should be equal to minus integral of del B by del T dot ds. So this equation is Faraday's law, which is simply telling you that EMF over the closed loop, okay, must be equal to minus d by dt of flux linkage, right. So the rate of change of flux linkage will be driving the EMF around this closed path. That is what this equation tells you. Then Ampere-Maxwell law will tell you that the magnetomotive force over a closed loop, which is given by integral of h dot dl, must be equal to the total current I surrounding a particular surface, the open surface through which this contour is being defined. So there will be a current I plus integral of del d by del t dot ds, which is how the displacement current is actually changing, right. And then you have 2 additional equations over the closed surface. So these were the closed loop, okay, and these were the open surfaces that we had considered. Over the closed surface, the way in which d dot ds, or the total electric flux, should be simply equal to the amount of charge that is enclosed, and similarly integral over the closed surface of b dot ds must be equal to 0, okay, because there are no magnetic charges out there to enclose. So these are the integral versions of the equations. These are fairly the same thing. So let me just write down this as the magnetomotive force, okay, must be equal to the current plus whatever the time rate of displacement. In other words, this is the displacement current that I have. So now I have all these equations. What I do is very simple. I imagine that I extend a path here which includes paths or points 1 and 2, and then I take this particular path. Okay, so I take this path, okay, and then this is the way in which I will take the path, and I will also assume that over this path the electric field E2 or the electric field E1 in the appropriate regions are not varying much. So let us call the path as having a length L and having a width W. Okay, clearly half the width lies above and half the width lies below this particular boundary. Okay, we will also assume that the value of L is not so large. I mean, you are not taking a kilometer long paths out there, you are just taking a path which is very, very short. It is just a few infinitesimal level paths that we are taking. Now over this path I will apply Faraday's law. Okay, so what do I get when I apply Faraday's law? Well, in order to apply the Faraday's law, let us also see that if I go from left to right and call that as the positive direction in which this is increasing, then I need to find out the corresponding tangential component of E2 that is obtained by projecting this E2 onto the path which goes from left to right, right. So when I do that one, I see that I can write this as E2 into L, or rather E2t into L, where E2t will be the tangential component. So this electric field here will have two components, right. So one component is the tangential component, which is what is important because this tangential component multiplies to the path length out there, and there will also be a normal component which we will call as E2n. This normal component will be perpendicular to the boundary. So therefore this is not really the path that you are looking at. So imagine again that this is my boundary, okay, and on this path, so let me keep this particular point here, and this is how my electric field is present. Okay, so this is my electric field. Now this electric field on this, if I take the path along this paper, okay, I need to first decompose this electric field into corresponding normal components. So you can see that the normal component is coming perpendicular to this paper, and because of this there will also be a tangential component out there. Okay, so there is a tangential component which is along the path that you are looking at, and there is a normal component which is coming perpendicular to the boundary, and because line integral always demands the tangential component, I write this as, or I am interested only in the tangential component. In region 2 the tangential component is E2t, and that is what I write, multiplied by the path length which is L, right. And on this side I have the normal component, okay, of corresponding to E2, and on this side I have the same normal component, but these two are in the opposite directions. Therefore even if I include them, because the signs here will be different and the magnitude of the normal component is the same on these two paths, okay, the normal contribution to this closed curve will be equal to 0. So the only thing which I am interested now is what is the contribution of this path and what is the contribution of this one. Again, if you decompose your electric field E1 into corresponding normal and tangential components, so this is the tangential and the normal components. So you have E1t and you have E1n as the tangential and normal components. You can clearly see that only the tangential component will contribute, because on this path the normal component will have whatever the contribution that will cancel out the contribution of E1 normal component of electric field on this path. So it is only the tangential components that contribute. Then there is also another catch. On this side we considered the traversing of the path as positive. Therefore if I move along this direction, then I need to consider the direction of dl to be opposite to the direction of the path along which I have taken in region 2. The net effect is that what I obtain here for the next, for the electric field in the region 1 will have a negative value multiplied by the tangential component E1t times L. So this is what I obtain for Faraday's law on the left hand side. But what is on the right hand side? On the right hand side I should have, I have a minus sign here, that is no problem. But then the total flux that is linking this closed loop, has to come because of the magnetic field that is coming out of this particular surface. So now I have actually taken this surface and I need to find out what is the normal component of this surface, okay, and integrate del B by del T onto that normal component. The total area that I have is L into W, and it is the normal, or it is the B component that is coming perpendicular to this loop that I must include over here. So let me call this as some B perpendicular component times LW, or rather del B by del T component times LW is what I am looking at, okay, and this is the equation that I now have. What I do is I divide by L on all sides. Okay. So when I divide by L on all the sides, what I obtain is that E2 tangential minus E1 tangential should be equal to minus del B1 by del T times W. Now what I do is I shrink this path going to 0. So I shrink this path, eventually I actually obtain, okay, or in the limit of W going to 0, I obtain above and just below the path. Okay. So which means that unless my magnetic field component B perpendicular blows up to infinity, the product here on the right hand side will tend to 0, and clearly the magnetic fields cannot blow up to infinity, because infinity magnetic field does not really make sense. Okay. We assume that all fields are finite, and therefore the right hand side completely goes off to 0. So giving you the first boundary condition that the tangential electric fields must be continuous. Okay. So the tangential electric fields must be continuous across the two boundaries that you have talked about. So let me just write that one. The first law, or the Faraday's law, tells you that E2t minus E1t must be equal to 0. So the tangential continuity of the electric fields is the first boundary condition that you are looking for. By the same logic, this second Ampere-Maxwell law will tell me that integral of H dot dl can be rewritten by following the same path that we actually followed. So I can write this one as H2t minus H1t, that must be equal to whatever the current that is coming out of this path. So this was the boundary, and this is the magnetic field that I am writing out there. Okay. So I get H2t minus H1t, and then whatever the current that must be coming out of this particular plane, plus whatever this current out of this plane, plus del D perpendicular by del T times LW. Clearly if I divide so this is H2t into L, H1t into L, that must be equal to the current plus this fellow. Now when I take, or when I remove L from all these equations, that is divide both sides by L, okay, I do not consider, or I see that this del D1 by del T becomes, or the L component goes away, and then you have del D1 by del T into W. Okay. Then if I now take the limit of W tending to 0, this quantity goes off to 0, simply because we do not allow for infinity fields D. So the contribution, as the loop shrinks down to a point, or loop shrinks down in such a way that you actually end up just having this kind of a loop here of infinitesimally small thickness, the contribution from the right hand side, or the displacement current, actually goes off to 0. Now should this current I also go to 0? Well, it does not have to go to 0. For example, if the medium here is a conductive medium, okay, then I can actually have currents on this surface. So all these arrows, or rather circles that I am drawing, I am also putting this one over here. So this is simply the case that the current is actually flowing on the sheet. So you can again go back to this boundary out here. Imagine that below everything is a conductor, and then this, I am keeping these pens over here, and the direction of these pens, you imagine that this is just on the surface, and these are the directions over which the magnetic field is coming. And since my loop is going up in this region, going down, and then going back up in this region, and coming again to the first region to complete the path, the current that I am interested is the one that is coming out like this. So if one of the medium is a conductive medium, then I can actually have the current component flowing along the plane or along the boundary, and we call this current as what is called as the sheet current. Okay. And we use a different symbol for that one. We use a symbol of K. So we use a symbol of K to denote that this is actually the sheet current. And what the conclusion that you have to draw from this by writing the same path and then trying to apply that boundary condition is that the tangential magnetic field components H will be discontinuous by the amount of this sheet current K, and you cannot rule out this sheet current unless the medium, both media happen to be only dielectrics. So if the medium happen to be, one of the medium happens to be a conductor, then there is a good chance that there will be a sheet current, and you have to consider that sheet current as the discontinuity component for the magnetic field. Now let us move on to talk about the conditions for D field and the B field. Imagine that I am actually keeping this what is called as a pill box. Okay, so I keep this pill box. Okay, there is a certain area on top, there is a certain area below, and you have to remember that these areas are always pointing in the opposite directions, because the surface area is actually governed by the right hand side rule. So if you go like this, then the surface on this plane is pointing up, and if you go in the bottom side, the surface will be pointing in the below direction. So the open surface components are up and down out there, and what you are interested now is the magnetic field component. So let us say at this point this is D2 and at this point this is D1. Okay, you again split the magnetic field into its normal and tangential components, and for this case you are not interested in the tangential component, you are only interested in the normal component, because that component is the one that would be perpendicular to the surface area. Okay, and there is a certain length or the height of this one, let us call this height of the pillbox as h. Okay, so integral of d dot ds over the closed surface, when you apply it over to these two regions, so this is medium 2, this is medium 1, what you obtain is that the normal component of the D field in the second medium, which is D2n, multiplied by delta s, where delta s is the area of this particular closed surface. This surface on top has a area of delta s, and if you go into the region 1, there will be magnetic field, but then the direction for the surface element has become negative, and if you now take that into account, you get minus d1n delta s, and this should be equal to whatever the charge that is enclosed. Again, there will be a case where the charges are enclosed, because the right hand side what you get the charge enclosed, or rather the charge density multiplied by, so the charge density, the volume charge density multiplied by delta s multiplied by h. Okay. Now if I take delta s out, or divide all sides by delta s and then let delta s go to 0, then what I obtain is qv into h, or rather not delta s. If I now let h go to 0, delta s is anyway gone on all these sides. So if I let h go to 0, this volume density is measured in coulombs per meter cube, and this h is measured in meters. Therefore the quantity that I obtain will be coulomb per meter square, and that coulomb per meter square will be the charge that you have taken and sprinkled on the surface. So if this is my boundary, look from the top. So if I put some charges on top of this one, I deposit some charges by some whatever means that I can, then this charge would correspond to the surface charge density, which we label as rho s, and we measure this one in coulomb per meter square. And as the pillbox shrinks in height, eventually just giving you two kind of surfaces of height h equal to 0, you see that the displacement vector or the d vector, the normal components of d vector actually become discontinuous by the amount of surface charge density. So the equation that describes the normal components d2n and d1n, the discontinuity or the difference between these two, must be equal to the surface charge density. This is intuitively kind of pleasing to us, because what does this mean? D2n is the flux density that is coming out of the second pillbox in the second region, and d1n is the flux density that is coming into it, right? So d1n can, because there is a minus d1n sign that we have considered, d1n is incoming, d2n is coming out. The difference in these two flux densities must be equal to the flux that is contained within that volume, and that flux is nothing but the charge that is contained. Again, if the two medium happen to be dielectrics, then if I send in some d1 here, d2n will be exactly equal to d1n, because there cannot be any leftover d values, otherwise there will be some charges, and for two perfectly dielectric medium there are no charges. But if one of the medium happens to be a conductor, then that conductor can have charge reside on its surface, constituting a surface charge density. In that case, the influx and outflux might be different, and the difference between the influx and the outflux will be exactly equal to the surface charge density that the surface of a conductor can hold. Finally, we have integral of b dot ds equal to 0, and you can very easily see that this simply leads to the condition that the normal component b2n minus b1n must be equal to 0. So these are the four major boundary conditions that we have described and we have discussed. The other boundary condition that involves del dot j equal to minus del rho v by del t, I will leave this one for you to figure it out, and this can happen between a medium in which both are conductors but have different conductivity, or one of the medium is a conductor and you have a conductor for the other case. So you will again have to write the integral form of this, that would be j dot ds will be equal to minus del d by del t dot ds. This is the continuity equation, and you can very easily show that the normal component Jn2 minus Jn1, when you evaluate on the two boundaries, that must be equal to 0, or Jn2 must be equal to Jn1. Okay, the conduction current has to be equal to that particular thing. So you can study this one at your leisure. I won't describe this one because we won't really be using this condition for the current density vector J as much as we use the boundary conditions for the other field components. The real value of boundary conditions is that once I calculate the electric fields in a particular region by using Maxwell's equations, then usually from the material properties I can calculate immediately what should be the field on the other side. Okay, and that will allow us to know, for example, if I have a mirror or if I have a glass and then light is coming in and incident on this particular glass, these boundary conditions allow me to determine not only the fields over here, which anyway I have determined, but will also allow me to determine the fields in the other region. Okay, because I can relate E1, E2, D1, D2, B1, B2, H1, H2, I can find out what are the fields in the other region. Then I can answer questions like, okay, if I incident 1 watt of power onto this glass, how much power will actually be reflected? What is the fraction of the power reflected? What is the fraction of the power transmitted? Right? If instead of having one boundary, what happens if I have multiple boundaries? And if I incident 1 watt power here, after 10 boundaries, what, or 10 boundary layers, what would be the power that would come out? Okay, so boundary conditions are very important when we deal with problems such as incidence, reflection of a wave, understand concepts like total internal reflections, Lenz's law, so on and so forth. And these boundary conditions that we have derived are fairly general. Okay, there are no unusual things going on except that there is a surface current density and there is a surface charge density. Both are little idealizations, but those idealizations will serve very well for us in order to understand how the fields behave from one point to another point. Thank you very much.